Question 8. Two charged particles are placed at a distance 1 centimeter apart. What is the minimum possible magnitude of electric force acting on each charge? Let us assume Q1 and Q2 are the two charged particles, and the separation between them is given equal to 1 centimeter. Then the electrostatic force between these two charged particles is simply 9 into 10 to the power of 9 Q1 Q2 divided by 1 centimeter square, that is 10 to the power of minus 2 meters square. Now the force depends only on, since the distance is given, the constant is there, the force only depends on the magnitude of the two charges. If the two charges are minimum, then the force is minimum. And we know that in nature, the smallest charge that can have an independent existence is the charge on an electron. So if we take Q1 equal to Q2 equal to the charge on an electron, which is the smallest charge possible, then the force will be minimum. So we'd be able to calculate the minimum force only when we substitute E for Q1 and Q2. And what is the charge on an electron equal to? 1.6 into 10 to the power of minus 19 coulombs. So we have E squared here, that is 1.6 into 10 to the minus 19 coulomb square, divided by, this becomes 10 to the power of minus 4. So when we solve this, this is 9 into, this is 1.6 square is 2.56 into 10 to the power of minus 38, and this is 10 to the power of 9 and 10 to the power of minus 38, and downstairs we have 10 to the power of minus 4. So when we solve this, we'll get a number approximately equal to 2.3 into 10 to the power of minus 24 newtons. Okay, let's move ahead. Question 9. Estimate the number of electrons in 100 grams of water. How much is the total negative charge on these electrons? Let us see how many molecules of water we have in 100 grams of water. So we could use the formula, the number of molecules divided by Avogadro's number is equal to the mass of the substance, so mass of the substance divided by the molar mass. Now we know that, so therefore N is equal to mass of the substance, that is mass of water is given 100 grams. Molar mass of water is 18 grams per mole. We multiply by Avogadro's number, which is approximately 6 into 10 to the power of 23 per mole. So we'll get the number of molecules in 100 grams of water. So just 6 threes is 18. So this is 100 by, or instead we could write 10 divided by 3 into 10 to the power of 24 molecules, which is 3.33 10 to the power of 24 molecules are present in 100 grams of water. Now, number of electrons in one molecule of water contains 10 electrons. Okay, 8 are associated with oxygen and 2 associated with hydrogen. So total we have 10 electrons. So one molecule has 10 electrons. Then how many electrons are associated with these many number of molecules? So we could easily calculate the number of electrons, let us say Ne will represent the number of electrons in 100 grams of water, would then be 3.33 into 10 to the power of 25. Okay, so these many electrons are present in 100 grams of water. Now let us see the total negative charge. Now charge is equal to, we'll use the quantization principle, charge is equal to the number of electrons times the charge on an electron. The number of electrons in 100 grams of water is 3.33, 10 to the 25. You multiply by the charge on an electron, that is 1.6 into 10 to the minus 19. And we get the charge, that's equal to approximately 5.33 into 10 to the power of 6 coulomb. Okay. Let's see the next question. Suppose all the electrons of 100 grams water are lumped together to form a negatively charged particle. So we have a negatively charged particle in which all the electrons are, it contains a charge equal to the charge of all the electrons in 100 grams of water. And we have already calculated that in the previous example. The charge on this would be simply 5.33 10 to the power of 6 coulombs. Okay, so and all the nuclei are lumped together to form a positively charged particle. There's a positively charged particle here, this one is negatively charged, this one is positively charged, and it will also be 5.33 into 10 to the power of 6 coulombs, because in a neutral molecule there are as many positive charges as there are negative charges. So in 100 grams of water there will be this much number of negative, this amount of negative charge and this amount of positive charge, because water in general is neutral. Okay, if these particles are placed 10 centimeters apart, okay, so we have to find the force of attraction between them. Okay, let's find the force of attraction between them. So the force of attraction can simply be found by Coulomb's law, that is 9 into 10 to the power of 9 times this much, we just multiply this 5.33 10 to the 6 whole square divided by the distance square, that is 10 centimeters, and 10 centimeters is equal to 0.1 meter. Okay, or you may write 10 into 10 to the power of minus 2, that is 10 raised to the power of minus 1, and then you square that. Okay, so this much amount of force. So when we solve this thing, we'll get a number of approximately 2.56 into 10 to the power of 25 newtons. Okay. Now there is one more thing that we have to calculate. We have to compare it with your weight. Now again, let's assume that you are of 50 kilograms mass, so your weight is 500 newtons. This is weight is m times g, and g we take roughly equal to 10 meters per second square. So the weight is 500 newtons. So if you compare this electrostatic force of attraction between these two parts with the weight, then you just divide by weight, you will get 2.56 into 10 to the power of 25. Well, when you divide by 500, you just divide by 5. This number you divide by 5 and divide by 100 here. 25 becomes 23. Okay, so when you divide this number, let's see how much value we'll get 2.56. 2.56 divided by 5, and we get 0.512, and that is equal to 5, approximately 5 into 10 to the power of 22. Okay, so a very large number. So that means the force between the particles, these particles, each having a charge equal to the charge of one type in 100 grams of water, that force, electrostatic force of attraction, will be somewhat 5 into 10 to the power of 22 times the weight of an average sized person. Okay, next we have 11th question. Consider a gold nucleus to be a sphere of radius 6.9 Fermi. We have a gold nucleus. We consider this to be a sphere of radius 6.9 Fermi in which protons and neutrons are distributed. Find the force of repulsion between two protons situated at the largest separation. So you may assume this is one proton. Largest separation means they are separated by a distance equal to the diameter of this nucleus. This is the gold nucleus. So what's the diameter? The radius is 6.9 Fermi. The diameter is then, that is 2 times the radius. Okay, that is 13.8 Fermi. Okay, this is the diameter. And this diameter is the distance between these two protons. There is a proton here, there is a proton here. Okay, so why do these protons not fly apart? First, we have to find the force of repulsion between the two protons, okay, situated at largest separation. This is the largest separation, so the force between two protons would then be 9 into 10 to the power of 9. The charge on one proton and the other proton has a charge similar to that of an electron, but a positive in sign. So it's 1.6 into 10 to the power of minus 19. You just square it, divided by the distance squared. Now, what's the distance between the two protons? That's 13.8 Fermi. Fermi is 10 to the power of minus 15. And then you square that distance. So when you solve this thing, now you could clearly see this one becomes 10 raised to the power of minus 38, and we have a 10 raised to the power of minus 30 here. So you are left with 10 raised to the power of 9, and that minus 9, and 10 raised to the power of 9 here cancels out with that, and roughly when you solve it, this answer turns out to be approximately 1.2 newtons. Okay, so this much amount of force, imagine this is a very large force per proton, because protons are extremely small entities, and for those two protons to have such a large force inside. Why there's this thing that's asked in the question, why do these protons not fly apart under this repulsion? The reason is that nuclear force, this is the electrostatic force of repulsion. Nuclei are held together by what are called nuclear strong forces. And nuclear strong force is roughly 100 times the electrostatic force. So that way you have a large force, nuclear force, that is responsible for keeping the two protons together. Okay, let's move to question 12. Two insulating small spheres are rubbed against each other and placed 1 centimeters apart. If they attract each other with a force of 0.1 newtons, how many electrons were transferred from one sphere to the other during rubbing? Suppose we have two spheres and we rub them. Initially they were neutral. When we rub them, one of them gains a negative charge. That's because of the excess of electrons, and the other gains a positive charge. That's because of the deficiency of electrons. So due to friction, some of the electrons from this second sphere have transferred into the first sphere here. Okay, so it has that many excess. Now they are kept, these two spheres are kept 1 centimeters apart, and the force of attraction between this negatively charged sphere and a positively charged sphere is given equal to 0.1 newtons. So the force is 0.1 newtons, and force is given by 9 into 10 to the power of 9. The charges on each sphere, okay, one has a positive, one has a negative, equal amount of negative charge. Let's consider the charge to be q square divided by the distance squared, and 1 centimeter is 10 to the power of minus 2 meters, and then you have to square it. Okay, now so this turns out this is 10 to the power of minus 1. You multiply it with 10 to the power of minus 4, that's equal to 10 to the power of minus 5, and then you divide by 9 into 10 to the power of 9. That is your q square, and that is 10 to the power of 9 goes upstairs. That is 10 to the power of 14 minus 14. So you have q square equal to 10 to the power of minus 14 divided by 9. When you take the square root, q is equal to 10 to the power of 7 minus 7 divided by 3. Okay, so this is the amount of charge that is present on each sphere. Okay, and we know that the charge on each sphere must be the number of electrons either in deficiency or in excess times the charge on an electron, and the charge on an electron is 1.6 into 10 to the power of minus 19. This is equal to the charge q. So n, we have to find out, this is equal to charge q, that is 10 to the power of minus 7 divided by 3 divided by 1.6 into 10 to the power of minus 19. Okay, so 10 to the power of 19 goes upstairs. When we solve this, and you subtract 7 from that, this becomes plus 19. You subtract 7 from that, that is 12, and then you divide, then you will find that the number is approximately 2 into 10 to the power of 11. Okay, this is the number of electrons that were transferred from one sphere to the other during rubbing. Now from this sphere, the right sphere, the electrons, I have taken this as positive, so the 2 into 10 to the power of 11 electrons were transferred from the right sphere to the left sphere. Okay, let's look at question 13. NaCl molecule is bound due to electric force between the sodium and the chlorine ions when one electron of sodium is transferred to chlorine. Taking the separation between the ions to be, so the separation between the ions is 2.75 into 10 to the power of minus 8 centimeters. Okay, centi means 10 raised power minus 2. This is 10 raised to the power of minus 10 meters. We have to find the force of attraction between them. So if you consider sodium atom and a chlorine atom, you know, chlorine, the sodium is the alkali metal. It will lose an electron, and that electron and therefore become a positive ion, whereas a chlorine will gain that electron and therefore become a negative ion. Okay, and these two ions will then attract by a force of electrostatic attraction. And that force we have to calculate. The distance is already given, and we know the charge. Charge for this is plus E, and the charge gained by this is minus E. So we just have to find the magnitude. The magnitude of the force would be 9 into 10 to the power of 9 times the charge on this and charge on that. That's 1.6 into 10 to the power of minus 19. You square it, divided by, that's 2.75 10 to the minus 10 meters. You square it. Okay, then we solve this, and you will get an answer approximately 3.05 into 10 to the power of minus 9 newtons. Okay, it says that state the assumption, if any, that you have made. Well, the assumption is that the sodium and chlorine ions act as point charges, even though in reality sodium ion and chlorine ions are not point charges. Also, in fact, the positive charge on sodium ion is not distributed uniformly, and nor is the electron negative charge distributed. So we have assumed that the distribution is uniform and that they act like point charges. Okay. In the next question, we have to find the ratio of the electric and the gravitational forces between two protons. So if you take two protons, this is one proton, there's another proton. A proton has a charge equal to E, charge equal to plus E, and of course a proton also has a mass. Okay, mass M, mass MP. I could write this is the mass of a proton. So because of the charges, there's a force of electrical repulsion between them, and that electrical repulsive force is simply K times Q into Q. That's E squared divided by R squared, if you assume R is the distance between these two protons. Then you would also see, since these protons have masses as well, so they must also have the gravitational attraction between them. So the gravitational force between them is simply G times mass of proton times mass of proton. This is M squared divided by R squared. So if you find the ratio, Fe by Fg, so what do you get? This R squared and R squared cancels out. This is Ke squared divided by Gmp squared. So the K value is 9 into 10 to the power of 9. Charge on a proton is 1.6 10 to the power of minus 19 coulombs. Then you square it, divided by, this is G. G is equal to 6.67 10 to the power of minus 11, universal gravitational constant, times the mass of a proton. That's 1.67 into 10 to the power of minus 27 kilograms whole squared. Okay, you put it in a calculator and you will get an answer of approximately 1.23 into 10 to the 36. Okay, so you could clearly see the electrostatic force is between two protons is about 10 to the power of 36 times the gravitational force between them. Extremely large force. We'll do more problems in the next lecture video. Thank you.